Okay, so let me give you a useful theorem on how to determine the number of divisors. So this is used to define the number of, sorry, let me try to write this a little neater. So number of divisors. Okay, so if P and Q are different primes, M and M are whole numbers, then P to the N times Q to the M has N plus 1 times M plus 1 positive divisors. Okay, so let me point out what does that have to do, what is that even trying to say? Okay, so let's take something like 2 squared times 3 to the first. Okay, so 2 squared is really 4 times 3, so we're really looking at the number 12. Now, we know this, we just did this earlier. If I break 12 up into its divisors, that's 1 times 12, 2 times 6, and 3 times 4, right? So there are 6 divisors, 6 numbers that go into 12 evenly. Oh, sorry, I'm just realizing I'm spelling this wrong all over the place. Okay, now what this theorem says, if I have the prime factorization for any given number, I can very quickly find out how many positive divisors there are. So in this case, I want 2 plus 1 from that exponent right there, and I want 1 plus 1 from that exponent right there. So that tells me that there are, 3 times 2, or 6 divisors. Okay, now that's kind of helpful if I'm trying to break up, say, 7,875. If I want to know how many different divisors come up in that number, right? We just figured out that that was 3 squared times 5 cubed times 7, right? So if I was to make a list of all the possible things that go into 7,875, I would want, so that number, so 2 plus 1 times that number, 3 plus 1 times that exponent plus 1. All right, so that's 3 times 4 times 2, so that's 24. So there would be 24 divisors that go into 7,875. All right, so you just take the exponent, add 1, multiply, and that tells you at least how many numbers you're trying to hunt and search for. Okay, so now that we've got a way to figure out how many divisors there are, let's talk about how we can figure out what those are, or what are the possibilities. Okay, so we're going to look at determining whether or not a number is prime. We only have to check prime numbers up to a certain point. And the biggest thing I want you to remember about this is the square root of n. Okay, so n is our number. If I take the square root of that number, I'm going to get something. All I have to do is check primes up to the square root of n. As long as I've checked primes up to the square root of n, then I know I've caught a list of all the possible factors that would be divisible into that given number. Okay, so let me get an example here. Let's check 397. So is 397 prime? Sort of a question here. Well, what is the square root of 397? And the square root of 397 is approximately 19.92 whatever. Okay. Now what that means is when I'm checking my factors, I'm giving myself a little space here to work. If I'm checking my factors, let me start with 2. Does 2 go in? 2's not divisible. so we're good. Does 3 go in? 3, in fact, doesn't. So if I add the digits up, I can see it doesn't. There's no need to check 4 because 4 is not a prime number. 5 is my next prime, and I know 5 does not go in. Since 2 and 3 don't go in, no need to check 6. Again, 6 isn't prime, so I don't have to check that. 7. Okay, so 7, if I do the 7 rule, so the 7 rule says take the last digit, double it. This one might be worth writing out so we could see this. So 39 minus 2 times 7. So 39 minus 14. And I get 25. I know 25 does not go in. So 7 does not go into 25. So I know 7 does not go into 397. So I'm at 7 now. Next prime number, let's see, we got 8. 8's composite. 9's composite. 10's composite. 11. So for 11, take the the even digits. So that would be 3 and 7 minus the even. Anyway, so I get 10 minus 9, so I get 1. So 11 does not go in. 12 is composite. 13. Let's see. We don't have a rule for 13, but if we just grab a calculator real quick, double check that. 13 is a decimal, so it doesn't work. Let's see. 14 we don't have to worry about because it's composite. 15 is composite. 16 composite. 17 is prime, and if we grab a calculator, we can check that. 19, again, checking that in the calculator. And at that point, I stop. I don't have to keep going because I only had to check prime numbers up to the square root of n. And since the square root of n is 19 point something, I only had to check numbers up to 19. And once I've checked numbers up to 19, then I've done everything I can. And now I know that 397 is prime. I want to do one more illustration of this. So let me take, let's see, 7. Let me take a number that we know has got some factors to it. So I think we'll do the 5 cubed times 3 squared times 7. So the 7,875. Okay. So let's take the square root. And we get, so the square root of 7,875, we get about 88.7. Okay, so what I'd have to do is I'd have to check the prime numbers up till 88. And once I've done that, I've found all the possible factors. And so that brings up another question, which we're going to go answer, and then we can address this a little bit more seriously. We've got the first prime up to about 19. How do we know what all the prime numbers are? Okay.